So that's just how you'd use Maple to deal with some of that stuff. Oh yeah, one more thing. So like I said, you have to give Maple these pieces. So when you go through the Laplace transform, often you're going to end up with something that kind of looks like this. So you have some function of s. Often in the denominator, you have these different terms that are multiplying together. It's just sort of the way the math works out for this. So let's go back and review a method of how you would solve this problem. So if you try to plug this in to Maple, it may or may not fail. It probably won't solve this. What you want to do is figure out little chunks you can put in. So you might want to put in something over s plus 1, something else over s minus 1, something else over s plus 2. So you need to use the method of partial fractions to solve this type of problem to get it to pieces that you can put in. So let's review what that is and go through a quick example. All right, so the method of partial fraction says I have this function, and I'm going to assume that this function can be described or written equivalently as some unknown c1 over the first term that appears, so c1 over s plus 1, plus c2 over s minus 1, plus c3 over s plus 2. So these unknown constants are just constants that are useful to me so I can solve this problem to get an equivalent statement. Right? They're not boundary conditions or anything like that. It's just unknown constants that I'm algebraically trying to solve for to get an equivalent formulation. So we write this, and then our job is just to solve for those constants. So what I would do is I would take this entire function here, and I would clear the denominator by multiplying by the left-hand side denominator. So I'm going to multiply everything here by s plus 1 times s minus 1 times s plus 2. So that makes this turn into the left-hand side s squared minus 3s plus 4. Right, the denominator is clear over there. And then on the right-hand side, we have c1 times s minus 1 times s plus 2. Because the s plus 1 cancels out. Then I have c2 times s plus 1 times s plus 2. And then I have c3 times s plus 1 times s minus 1. Right? So just algebra there. Now let's factor things out or multiply things out so we can see how this consolidates. So again, we have s squared minus 3s plus 4. So now if we multiply this stuff out, what do we get? Just make sure I get this right. Where did I go? OK, so we have c1 s squared plus s plus 2. Did I do that wrong already? c1 s squared plus s plus 2. Plus c2 s squared plus 3s plus 2 plus c3 s squared minus 1. Okay. So now that the same thing we used, we were solving for like our particular solution, and we need to use matched orders or matched powers. We need to do the same thing here. Yeah. Yeah, I think you're right. It didn't seem quite right to me. Yeah, my notes are wrong, so I think it's minus. OK, any other? OK, so we need to just use the match power. So we would go through and we'd say, OK, what is multiplied by s squared? What is multiplied by s to the first and s to the 0th? And collect like terms, and then we have 3 equations for our 3 unknowns. So we have here on the left-hand side, we have 1 for the s squared, we'd have a 1. On the right-hand side, we have c1 plus c2 plus c3. Okay, to the first power on the left-hand side, we have minus 3. Then we have c1 plus c2 And then, sorry?
Should be 3C2.
Did I do that? C. Yep, you're right. The hardest thing is literally algebra. C2. And then the last one would be, let's see if I got this. No, maybe wrong. So 4 is equal to, it should be minus 2, right? Minus 2C1 plus 2C2 minus C3. Let's see, minus 2C1. Yep. Okay, so you have 3 equations, 3 unknowns. You solved it algebraically, and you can rewrite an equivalent formulation for that, for this statement up here, that is in terms of stuff that you can actually plug into your tables, right? That you can go to the table or plug into Maple and get an answer back. Okay, so we just say this is 3 equations and 3 unknowns. So we're kind of good to go there. All right. Okay. So that's the general method. I mean, it's probably, you're probably remembering back to like freshman year for something like that or before that. But just a refresher on that. The next thing is a couple other minor points. I don't want to write S a whole bunch of times, so I'm just going to do this. So let's say we have slightly different situations where you have a factor, do it this way. So you have a factor, let's say, up here that is some term squared. So how do you deal with that when we're writing out the method of partial fractions? Well, if you have a term that's squared, when you're writing it out, you need to include that term and then any power that's below it. So here we have a squared term, so we need to write, this one s plus 1 squared. Oops. This one s plus 1 squared, and then s plus 1. If we had a cubic term, we'd have to write 3, and so on. So that's just something to point out. And then you end up with this equivalent statement here. In the case where you have a polynomial in the denominator, so that might be something like this one here. You have s squared plus 2. That's a polynomial. We would have to write an equivalent polynomial here that's 1 order lower. So if it's s squared, we have to write c1s plus c2. If it was s cubed, be c1s squared plus c2s plus c3, right? So you have to write it out that way. And then you end up with the same type of thing. So you're just trying to come up with this representation of the constants that lets you simplify the problem.